Welcome to Quantum Curious, and in today's lecture, I'm going to discuss another distribution, that is the probability distribution of the field, called Poisson distribution of the field. So in the previous lecture, we discussed the distribution followed by the thermal fields, that is the Bose-Einstein distribution, and we saw that what are the implications of that particular distribution, and we saw that it is that the thermal fields have that photons in the thermal fields have the tendency to be bunched up, and it means that they during the detection process they usually have the tendency to be detected multiple photons at the same time. So in this video, we will just see that how the Poisson distribution has some physical implications, like the Bose-Einstein distribution in the case of the thermal field. So we will see that the Poisson distribution is followed by some kind of fields like coherent state that have uh, like physical realization in the form of the laser field. So we know that laser fields have usually random number of photons, but their phase value is quite constant throughout throughout their travel and during the detection. So we will see these kind of implications in in this lecture and in the upcoming lectures and videos. So first start with the form of the Poisson distribution. Uh, so many of the people might have seen this Poisson distribution in their courses. So we know that it is used the to describe the phenomena or events that are usually random, but they usually occur at some fixed interval of time. So we can calculate some interesting properties of the field through this Poisson distribution. So the fields like coherent fields and the fields that describe the laser follow this Poisson distribution, and the photon detection detected at the detector follow this Poisson distribution. So that is why many of the fields in experimental realizations can be described by this probability distribution. So our first task is to calculate the first moment, that is the average photon number, through this Poisson distribution. So again, using the similar formula of the statistical moment, that is the first statistical moment, or you can say average photon number, putting in the mathematical form, and in order to solve this, we can cancel out some common terms from numerator and denominator, and uh, taking common out in some terms in order to make this form and an exponential form. So we know that it is an exponential of average photon number. So the both exponentials are going to cancel each other. So we are left with the average photon number that we started with. So uh, the Poisson distribution have first moment is equal to the average photon number. So similarly, we can calculate some higher statistical moments. So like we can calculate the variance, and the first step in for the variance to be calculated, we have to calculate the average of the n square. So again, using same probability distribution, that is the Poisson distribution, putting in the value and canceling out the common terms from numerator and denominator, we end up with this form. So we have to solve this sum. So let's look how can we solve this quantity. So we can change here our variables from n to k. So we are going to uh, equate k is equal to n minus 1, and n is equal to k plus 1. So changing these variables in the sum, And we can do that for simplification every time. So again, simplifying the expression, we end up with this. So we know that this will be going to be an exponential of the average photon number. So this is fine. So the problem is here. So we have to solve this first term or this first sum. So again, canceling out the common terms from the denominator and numerator, we are end up with the k minus 1. So again, changing the variable and the sum limits, we are going to end up with this form. So here is j plus 1 power and the denominator is j factorial. So we want to make it the same for the numerator and denominator. So we will take common out uh, the average photon number term, and we have this amazing quantity, and we know that it is an exponential of the average photon number. So putting all these values that we have determined here into the above expression, we end up with this. So taking in the out the terms that are outside the parentheses into the parentheses, we will have this expression for the n square average. So again, putting this value in the formula of the variance, we can see that we end up with the average photon number. So this implies that the fluctuations of the field are not quite large and they surround the average photon number. So the field following the Poisson distribution uh, will is going not to be that much fluctuated in terms of the photon number, and uh, it will uh, it will give the fluctuations just about the average photon number. So in the case of the thermal field, we saw that the photons, average photon, or you can say the variance of the field was quite large, and it means that the the field has very large fluctuations in terms of the average photon number. But in that case, for the Poisson distribution, the field does not have that much kind of uh, fluctuations. So we have variance, and we can use this value to calculate the correlation function. So again, we have the form of the correlation function as always, and we will put the value of the variance that we calculated above in below mathematical form. So we end up with a value of 1 for the correlation function. That is the second order correlation function. So it tells us that the photons in the field that is following the Poisson distribution uh, are quite individual, and they are not relating to each other that much. But as opposed to this case, we saw in the thermal field that the correlation function was telling us that the photons in the field are going to be bunched together, or they have the tendency to be detected at the detector at the same time or together. So this is quite an interesting result, and it is very different from what we saw for the thermal field. So again, we can verify this result. So we know that the correlation function has this value for in general, and we know that for the Poisson distribution, uh, it is going to be is equal to 1. So we can see that the the average of these operators is going to be individual, the average of the pairs of the operators. So we could interpret it as the photons in the field are have some kind of individuality in the case of the Poisson distributed field. So here is an uh, distribution graph for the Poisson distribution and thermal field. So you can see that the peak, it it is representing the Poisson distribution, and it is not that much wide, and it is surrounded or it is surrounding a particular number, that is the 20. So the field is not that much fluctuated, and it is has very narrow range in terms of the photon number. And in opposed to that, uh, the dashed line is showing the thermal field, and we could see that it has very large number of photon number from 0 to 50. So in Poisson distributed fields, the a field is going to be very narrow in terms of the fluctuations of the photon number. But on the other hand, for the thermal fields, the range of the photon and the fluctuation is going to be very large. So this graph is telling us that kind of thing. So here is another parameter, that is the Mandel Q-parameter, and it tells us the uh, distribution of the field in terms of the three categories, that is the super-Poissonian, sub-Poissonian, and Poissonian. So if it has Q is equal to 0, that the field that we have is has Poissonian distribution, and it is if negative, it is has negative, or it has sub-Poissonian distribution, and if it is positive, uh, then we have super-Poissonian distribution. So let's assume this expression, and in the case of the Poisson distributed field or coherent field, so the for the coherent field, the correlation function have values equal to 1. So this Q parameters will be going to be 0 for that particular field. So it lies in the Poissonian distribution. So Poissonian distribution fields have photons that are very individual, and they usually do not have that much correlation with each other. But on the other hand, if we put the value is equal to 2, the Q value is going to be positive, and it corresponds to the super Poissonian distributed field. And this is the case for the thermal field, and thermal field have super Poissonian distribution, and the photons in this field has much more tendency to be to much more tendency to be stick together and to be detected together. On the other hand, for the Fock state, if we put the value of the correlation function, the Q value is going to be negative, and it corresponds to the sub-Poissonian distribution. And in that case, the photons usually show the property of the anti-bunching. So in this case, if we know the variance and average photon number of any field, we can categorize the given field on the basis of this parameter. So today we saw that what are Poisson distribution, and how the fields that follow this kind of distribution have some physical implications, and we saw how it is different from the thermal fields. So in the next lecture, we will see that what are coherent states and why we call them the semi-classical state, and we will see that what are their properties and how they differ from the fields that we have studied so far. So thank you for listening up to this.